soạn ánh sáng. Sao mỗi hôm nay soạn ánh sáng đâu nè. Thầy cho qua một cửa tia sáng đã mà.
I think we can start after 5 minutes. How are you today? Good? Too much football yesterday? Did you watch some matches yesterday? Yes? How many matches? Two matches. It was hard, right? Hard having class started early today. This applies also for me. So we start from 7:30 until, if I remember well, until 10:30. Something like that? Huh? 15 past 10. Okay, it's good. So I hope that we stay focused. There's only about half of the students who are here, I suppose. We wait a little bit more. Some of you know me already, right? Do I have to introduce myself?
Yes.
Yes? Okay. I see some students in the badminton lab. Do we have a football club? How many people are in the club? Do we have a football team for UST? Trường mình có câu lạc bộ bóng đá đúng không? Bạn nào là chủ tịch thế nhỉ? Who is the leader? Không có à? Sorry, can you help me to close the door? Yeah. Maybe you become more familiar with this auditorium. But last year, we didn't have that. Yeah, last year. I mean, we still have the same room, but we do not have a new system like this, new system of camera, new system of projector. So I hope that this would help us stay more focused on the lesson. So I will start by introducing myself first. Some of you already know me, maybe some not. My name is Nguyễn Hồng Nam. Actually, I'm the I'm the director of the General Education Department. I mean the department which is taking care of you before you go to the second year and the third year. So my office is 202, and should you have any question, please feel free to come to see me in my office. So 202 of this building. I mean any questions related to the academic stuff, okay? Not related to other things. I will take care of the thermodynamics. This part is harder than the mechanics. So I can tell you, so we should stay more focused on this. Why I say harder? Because for fundamental mechanics, you learned it during your secondary school, secondary study, and during also high school. Okay? You got it during the grade 10, and you repeated it during also grade 12. So you have a lot more time studying mechanics than thermodynamics. For thermodynamics, you learned it during the grade 10 only, and it was not included in the national exam. So a lot of you forget. Do you still have any idea regarding ideal gases or kinetic theory of gases? Yes, still. How many people still have the knowledge? PV equal nRT. Ever heard about that equation? How many people? Ideal gas law. How many people know the ideal gas law? Vì luật thì lý tưởng ạ, bao nhiêu bạn biết đấy? Only one? Two? How about the first law of thermodynamics? How many people know when we talk about the change in internal energy of a system? How many people know? Only one? You see, you learned it. I read the textbook. You learned it already, and then you forget everything. So we have to start from the beginning. Good. So I will start the first content of today. Firstly, I will give you some overview and also some basic concepts of thermodynamics. Okay, I want to be sure that we speak the same language in thermodynamics. I will give you some terminologies so you understand what we are talking about, and then we will continue with some notions, okay, very basic notions, maybe you know, maybe you forget already, regarding temperature, heat, and also the first law of thermodynamics. Then we will start the very big part, which is a little bit difficult when we talk about the kinetic theory of gases. And we will finish with the second law of thermodynamics and applications, some applications of the second law of thermodynamics. So this is the whole content, okay, of the part of thermodynamics. We have 4 sessions working together. I think, if I am correct, we have a little bit less than 12 hours working together. So it's not much. For the evaluation, I repeat it once again. I mean, you do not need the recorder. This is for nothing. If you stay focused, if you participate in the class, you do not need the recorder. Yeah. I'm sure that you do not have enough time listening on of what you have recorded. For the evaluation, so the attendance, if we take 10%. Of course, I cannot check attendance in the auditorium. But please remember that we have tutorial classes, so please be present. And I would like to remind you also, the final exam is prohibited for those who are absent for more than 30% of the classes. So please be aware of that. The midterm exam and also the participation in tutorial classes will take 30%. Yeah. This one is very important. If people already worked with me, so you understand what do I mean. Okay? I always give you bonus during the tutorial class. The final exam would take roughly 60%. And for the bonus, I give you 10%. So if you sum up, you have 110%. Yeah, more than 100%. It means the maximum point that you can get is 22 out of 20. I never seen it before. So try your best. Okay? Is it clear until here? You can stop me anytime if you like, okay? I have any questions so far. Good. For the textbook, I use this one. If you like, maybe you have it already, or if you like, I can upload it on Moodle for you. This is a very heavy book. If you have time reading it, please. Otherwise, I also summarize the main things in my slides. It could help you. So, the very famous textbook, Fundamentals of Physics from Hallidays and Resnick. So for the first part, the overview and basic concept, what I expect from you is that after this class, you should be able to remember the historical development of thermodynamics as a branch of science. You should be able to understand, okay, terminologies in thermodynamics. So we have to be sure that we speak the same language in thermodynamics, okay? I mean in thermodynamics. So you should be able to understand some terminologies, important terminologies. And also understand some basic concepts in thermodynamics. Good. May I propose that you find your places quickly. So let's start with the term thermodynamics. How do we translate? Yes, nhiệt độ lực học. So we see we have the part of thermal, which stands for heat, right? And dynamics, which is the movement. So, if we see this board, we know that we are studying the energy transfer as heat. Okay? The energy transfer as heat. So we study the effect of the energy transfer as heat. Good, which is very easy. And if we look around us, there are a lot of applications in our daily life which applies the principles of thermodynamics. A lot. If you look at your kitchen, you will see everything is engineered using the principles of thermodynamics. We have the oven, for example, right? We have the oven. We have even here, what do we have? Even here. Yeah, air conditioner, which is a very famous application of thermodynamics. I can tell you, without it, during summer, there will be no class for you. There will be no class. So we see, thermodynamics is everywhere, okay? A lot of applications in our daily life. I can give you some more examples. So this one is very common, right? A thermometer. So you use a lot of thermometer, especially during the COVID. Everyone has one at least. So this is also engineered using mostly the zeroth law of thermodynamics. Okay, there are also other laws of thermodynamics involved, but mostly the zeroth law. So in thermodynamics we have 4 laws, okay? The zeroth law, the first law, the second law, and the third law. For the zeroth law, of course, we will go from the zeroth to the second law. For the third law, we will not mention about it, but I think you know it already. For the zeroth law, we talk about the thermal equilibrium. For the first law, we talk about the change in internal energy. For the second law, we talk about entropy. Okay? Have you ever heard about entropy? Yes? Okay. We try to explain it in detail. And for the third law, we talk about the absolute zero. So the 0 Kelvin and phenomena associated with the absolute zero. Good. So very common application of thermodynamics. So we have the thermometer. We can also have the microwave oven also. So we have the involvement of the zeroth law, of the first law. We have the vacuum flask. I don't know if you have one here. No? And we have the HVAC system. Heating, ventilation, air conditioning system. So we call it in short HVAC, okay? This system, we call it HVAC. So in industry, you can even find more. For example, the magnetic cooling or the thermal power plant. Yeah. The plants, these also apply a lot of laws of thermodynamics, or you can find it in the jet engine and also in the heat engine. I think you use the heat engine every day, right? In your motorcycle. Yeah, motorbike. So you use what we call the heat engine or simply the engine. But actually it's a heat engine. We are going to talk about it deeper in my slides also. So now, a little bit of historical development of thermodynamics as a scientific discipline. We have the first name, which is Otto. So we have even Otto Cycle. He was a German scientist and he was the first one who built and designed the first vacuum pump. Okay? So we have Otto in 17th century. Then we have Robert Boyle, okay, and Hooke, and they built an air pump also in the 17th century. I think you heard about their names already, right? Do you know the boy Marriott law during the Great Hand? Yeah, some remember, right? Các bạn nhớ đến lời boy Marriott không ạ? Đúng không ạ? Học rồi ạ. So, this guy, Hook, ever heard about it? Ever heard about this name? Yes? Okay. And then, Denis Papin. I pronounce it in French. We pronounce Denis Papin. French is a little bit weird in the pronunciation. And he was the first one who built a steam digester, which applies also the thermodynamics. Some of you know French. Ở đây có ai nói tiếng Pháp không ạ? Not yet. You will. After 3 years studying here, you will speak French also. We continue. Then, in very late of the 17th century, we have Thomas Savery, who built the first engine, which is very important. So we have the first engine very soon in the 17th century. We already have the first engine. But only until Sadi Carnot. So he was very famous. Okay. Also another French engineer. He was called the father of thermodynamics. So until Carnot, he published a discourse on the heat, power, and energy, and engine efficiency. Now we know much more about him than all the names, and he was called the father of thermodynamics for some reasons. Okay, later on, more closer to us, we have Gibbs. I think you heard this name in your chemistry subject. Chemistry subject. Gibbs. And then later on, in the early of 20th century, we have some names. We have Lewis, we have Randall, and these we have, I don't know if I correct, if I pronounce it wrong, Guggenheim. And then here, these people, they applied the mathematical methods of Gibbs to the analysis of chemical processes. So we have some names. So you see, the thermodynamics was not something new. It was developed even in the 17th century, and it is still developing until now. We are studying it, we are still studying it, we are still studying its applications, and we are still using applications of thermodynamics every day. Okay? Now, we go to the part of some basic concepts. Firstly, I would like to talk about some terminologies. Before starting the thermodynamics, we should know what is an open system, what is a closed system, and what is an isolated system in thermodynamics. Do you have any idea What is an open system in thermodynamics? In thermodynamics, when we say, okay, my system is an open system, or it is a closed system, or it is an isolated system, this is very important. So any idea about that? What is an open system?
Okay, so in my opinion, the open system is a system. It works open. I have example like our plant is provide oxygen is in an open environment, and the closed system is like in the production of food in some factory like Italy or Latin water.
Not really in thermodynamics. When we talk about an open system, we consider its energy and its mass. Okay? We consider the energy transfer, maybe in the term of heat, maybe in the terms of work, and also the mass transfer. So in an open system, what we have is that both energy interactions and mass interactions can take place in an open system. So there will be energy transfer and there will be also mass transfer. Okay? It's like when you do some experiments in chemistry and you let it open, there will be a mass transfer between these pipette and the environment. So it can exchange both energy and also the mass. Good? So in a closed system, what do we have? We have only the energy interaction and no mass interactions. So I have the same pipette, but now I close it. What will happen? So the substance that I have here will remain inside. Okay, will remain inside. There may be only the heat that will be transferred in and out. Yeah. So I will have a closed system. For an isolated system, I think you can imagine already, right? Then no energy interactions and no mass interaction that will take place. It corresponds to our case, so I still have the same pipette and then I close it, but I also isolate it. Yeah, I have an insulation. Good, I put it in an insulation. So that there's no heat transfer in and out of my system. And also no mass transfer in or out of my system. Is it okay? So we have open system, closed system, and isolated system. Good. Now, during the homework, when you do some homework, when you do some problems, so that you recognize what is a closed system, what is an open system, or what is an isolated system, right? When we talk about open, closed, or isolated system, we talk about the transfer of energy and the mass. Good. We should also have the terminology of macroscopic system and microscopic system also. Macroscopic system is concerned with the effects of certain number of matter, and these can effects can be perceived by human senses. Of course, there's no clear boundary. There's no clear boundary between a macroscopic system and a microscopic system. But what we use is our human senses. For example, we can have the pressure, right? Because we can sense the pressure. We can have the volume or the temperature of our system. We can determine the density or the composition or the viscosity, or again the color, the refractive index. So we can measure it, we can sense it, right? So we call these properties the macroscopic properties, which are associated with a macroscopic system. Good. And for the microscopic system, yeah. So in a microscopic system, it is concerned with the effects of the actions of molecules. Yeah, we talk about a much smaller scales, the scales of molecules. And these effects cannot be perceived by human senses, for sure. Associated with the microscopic system, we have microscopic properties. So, for example, we have monomers, we have the velocity of atoms or molecules. Okay? We have the momentum, we have the kinetic energy, for example. So in this class, we will study both macroscopic system and microscopic system. For the macroscopic system, we can study, we can discuss about it during the first law. And for the microscopic system, we will discuss about it during the chapter of kinetic theory of gases, the big chapter. Any questions so far? If not, we move on. We have another two concepts, what we call intensive properties and extensive properties. Okay? The intensive, it has another name. We call it intrinsic properties. Intrinsic properties. So these are properties that are, let's say, independent of the mass of the system. For example, we have the boiling point of a substance. So this is independent of the mass of the substance. Right? We have the color of a substance. Now we have the temperature, or we have the luster, or we have the hardness. Okay? These are some examples of the intensive properties. For the extensive, or it has another name, extrinsic properties. Okay? Then these properties are dependent on the mass of the system. So for the extensive or extrinsic properties, so these properties are dependent on the mass of the system. For example, we can have the volume, so, and the mass itself. So it depends on the mass of our system, right? the size, okay, the weight, and the length, also the length. So these are some examples of the extensive properties. Nếu như mà các bạn tra từ điển cái từ intrinsic này nó có nghĩa là nội tại. So it has it in itself, nội tại. Nó bản thân nó đã có rồi. Là cái tính chất mà bản thân nó có, đúng không ạ? The body point of a substance. So it is not dependent of the mass or the temperature, right? Or the color. Is it okay? Too much terminologies? Will you catch it up? If yes, we can continue. There are some more terminologies that are very important, and you will see that I will very often talk about it, which is a state. A state. What is a state in Vietnamese? Good. A state. And we define a state by specifying values of a set of measurable properties sufficient to determine all other properties. Here I give you an example. So a state of a fluid system can be determined if we know the volume of the system, or we know the temperature of the system, and we know the pressure of the system. If we know the three properties, we should be able to determine the state of the system. Good. For example, when I say that, okay, my fluid is in the state number 1 here, so it will have a pressure, it will have a volume, and also it will have a certain temperature. Good. And when we change from one state to another state, we say that we do a process. So any change of the state of the system, we call it a process. Tiếng Việt là gì ạ? Chu trình. Not quá trình, not quy trình. Quy trình là procedure. Process, okay? In process, a very famous book, Vietnamese famous book, translated from this textbook of Halliday. They use it, if I remember well, chu trình. The process. Okay? So you know that when a system changes its state, we say that the system does a process. And then the process path, actually this is the way, okay? The state, the initial state changes to the final state. We may have infinite states through which the system passes while going from initial state to final state. Here I mean that to go from the state number 1 to the state number 2, we can go like this, so we do a process, or we can go like this, we do a process, or we can do like this. Okay, we have infinite ways for us to go from state number 1 to state number 2. Is it okay? So we have stage, we have process, we have process path. Good? Shall we continue?
Yes.
Or I stop you a little bit. So, to check. What is a closed system then? I put you back a little bit. What is a closed system? I'm asking you because I see that you do not stay focused on the thermodynamics. You can go out if you like. Okay? When you stay here, you study thermodynamics, not other things. So can you answer me, what is a closed system? I'm checking if you are following.
So a closed system is not open one. So a closed system, which means only the internal energy in that system on the field, and this has no interaction with this other process and energy.
Who can answer it correctly? Who can help me answering the question?
I think the closed system is a system which only energy interaction.
Thank you. In a closed system, only energy transfer that can take place. We continue. This one is also very important terminology: reversible process and irreversible process. You are going to see it when we talk about the entropy. And you will see that in reality, there is no reversible process. But then, okay, in theory, we still consider some processes reversible. Yeah. So a reversible process is a process that can be reserved, okay, in order to obtain the initial state of the system. So when a system changes from the initial state, it can still be back to the initial one. For example, this one, we call it a reversible process. In an irreversible process, we cannot find the initial state. And this applies for every real process in our daily life. When you drop an egg, okay, when you drop it, and I don't think that you can recover the egg from the initial state anymore. But you can try it. Or when you crash a car, it cannot return to the initial state. Các bạn thử đâm xe mà xe nó sẽ không ở trạng thái ban đầu, nó không quay về trạng thái ban đầu, trừ khi các bạn bỏ ra một khá số tiền. Nhưng mà chắc là nó cũng không sẽ ở cái trạng thái là mới. Good. So please remember that some can be considered reversible processes. Yeah. To simplify things, we want to study something that is more simple first, and then we extrapolate what we know, we apply what we know to the real situation, which is more difficult. Yeah, reversible process. I give you an example here. For example, the uniform and slow expansion or compression of a fluid in a piston. So when you compress a fluid in a piston, okay, in a piston, and then you expand it, so you might, when you compress it, what do you change? You change the volume, right? You change the pressure, maybe the temperature. When you expand it, and the piston goes to the initial place, you might return the initial volume, you might return to the initial pressure, and maybe the temperature also. And for the irreversible process, there are many. For example, the heat transfer. For example, the diffusion of electricity flow through a resistance. And what I told here in reality, no process is really reversible. We are going to see it when we talk about the entropy, the error of time. We will study some more terminologies and then we make a break. Here, we talk about some equilibrium of the system. In thermodynamics, we should talk about the state of equilibrium. So we have the thermal equilibrium. We may have the mechanical equilibrium, chemical equilibrium, or the phase equilibrium. In the thermal equilibrium, we have it when, for example, we put a hot water here, a hot object here, with a cold object here. When we have the same temperature in both sides, in both objects, we can say that we have a thermal equilibrium. So in mechanical equilibrium, for example, we put an object here up to the hill and it remains stable. Then we can say that we have mechanical equilibrium. In chemical equilibrium, okay, when we let the substance number 1 react with the substance number 2, when do we have the chemical equilibrium? So let's say I have the substance number 1. I put it for it to react with the substance number 2, and then I have two products. Number 3 and 4. When do we have the chemical equilibrium? So when the masses of the substances do not change. When the mass doesn't change. Okay? The mass of the product and also the mass of the initial substance do not change anymore. Then we say we have the chemical equilibrium. For the phase change also, so the thermodynamic equilibrium, we have it when there is no tendency for the state of a system to change. Good. We can have other example. For example, the gas in a cylinder with a movable piston. So, this will be an equilibrium if the temperature and the pressure inside are uniform and if the restraining force on the piston is sufficient to keep it from moving. Good. So we have our cylinder, we have our piston. If the piston doesn't move anymore, what do we have? We have a stable temperature, we have a stable pressure. Good. So if we look back, we have a lot of terminologies and I hope that you will remember it. What do we have? We have open system, we have closed system, we have isolated system. Okay, now you know what is it? We have macroscopic system and macroscopic properties, also macroscopic system, macroscopic properties. We have intensive properties and extensive properties. Good. We have the state associated with the state, with the change of the state. We have the process and process path. Okay, and we have reversible and irreversible processes. And then we have thermodynamic equilibrium. So this part, there are a lot of terminologies for you to remember. A little bit boring, but I want to be sure that you understand all of the terminologies when I mention about it. So I think we can take a break of 10 minutes and then when we are back, we will study something that is more interesting. Okay? Which is the temperature, heat, and the first law of thermodynamics. So for people who are still sleepy, you can go to the toilet and then you can clean your face. Yeah. We see each other in 10 minutes.
nha. Bố bảo đấy.
chơi chán đời lắm.
Thank you. So already woke up? Shall we continue?
Yes.
Good. So we go to the second part of this session. we will discuss about the temperature, heat, and also the first law of thermodynamics. Okay, before that, I would like to remind you that all of your computers are served to study thermodynamics. These are not served for games, not for Facebook, not for football. You can do it later, okay? Yeah, I suppose that you do not play games, at least during my class, because you can do it at home. I do not check attendance, so you do not need to stay here playing games. And secondly, you can stop me anytime if you have any question related to my slides. I ask for your interaction this time. When we already know some terminologies, which is good because in this part there's mostly no interaction, but this part I ask you to answer some questions, to give me some examples. Or for example, here after this part you should be able to understand the concept of temperature. Of course, we talk about temperature every time, but it is still good to remind you what really is temperature, and also the notion of heat. Okay, the notion of heat, and the first law of thermodynamics. What is the first law? You learn it and then you forget it. Now you learn it again. A very important law. Very quick. The temperature is the degree, or we call it the intensity of heat present in a substance or object. When we say the temperature, we have a concept of the hotness or coldness. Okay? When we say, okay, it's very hot, so we already link with temperature. So the temperature is used to express the hotness of a substance, of a radiation, of a matter. And this is one of the 7 SI-based units. I like an S here. The first question, what are they? What are the 7 SI units that I mentioned? Someone knows? 7 đơn vị cơ bản trong cái SI là gì? First, what is SI? SI. Yeah, what is SI?
Alright, so SI is just a French abbreviation standing for Système International. The first one is the length with the base of meter. The second one is weight, with the base of kilograms. After that, we have the area with the base of square meter. No. Not really. Maybe volume. Maybe volume with the liters. For electricity, we have the voltage.
Kilowatt per hour.
Ampere, yeah. Ampere. Or. And also, one more thing,
For the light, what do we have?
height.
reflective.
There must be temperature there. That is Kelvin. Kelvin? Yeah. I guess it's 5 or something.
So two stream missing. So we have here, we have and here, we have kilogram, and then we have what else? We have Kelvin, pi, so stream missing. Molecule.
Mole.
More, yeah, more. One more. More is one of the 7 exercise units.
Fine.
Second. Yeah. So the 7 SI unit, we have the temperature. Very good. And we also know that
the temperature is in the SI unit, it is measured in kelvins, right? But then we usually mention about Celsius more. Okay, Celsius, because originally we used Celsius first, but then, truly speaking, Celsius do not have much meaning in terms of physics, because we have negative temperature. That's why Kelvin's proposed a conversion to convert degree Celsius to degree Kelvin. And starting from this, we have the lowest temperature starting from 0, not from minus 273 something. Good. So this is the conversion of temperature scale. So I will not mention it about it deeply in detail. But you know that, okay, our universe today is around this temperature. So this is the temperature of the surface of the sun, and this is the temperature when the universe just after, at the beginning, very hot. And this is very close to the absolute 0. This is the lowest temperature that human could record until now, very close to absolute 0. When we talk about temperature, the first thing we should talk is the zeroth law. Zeroth law. So this law says, if bodies A and B are each in thermal equilibrium, so now you know what we're talking about, the thermal equilibrium, okay? If bodies A and B are each in thermal equilibrium with a third body T, then A and B are in thermal equilibrium with each other, which is very simple, right? It's now, when you hear it, it's like obvious. So it says that, okay, here I have a certain temperature. Here I have a certain temperature. If the temperature of A and B is the same, so A and B should be in thermal equilibrium. It means there's no heat transfer anymore between the two bodies. Okay? The question here is that why it has the name of zeroth law? Do you think it's weird why we do not start by saying, okay, the first law? It's not normal, right? When you name something using the number 0 instead of number 1. Why? It has a reason. Why? Someone knows? Đúng không ạ? Các bạn có bao giờ các bạn đánh số từ 0 đúng không ạ? Giỏi quá. Có. Can you close the door, please? So it has a reason. Vì sao ta gọi là định luật không ạ? Actually, this law came to light in you see it's very late. At the beginning I told you that the thermodynamics started from the 17th century, right? But this law came to light in the 20th century, right? Long after the first law and the second laws had been discovered and numbered. Yeah, very late. And because this is the basics of all the laws, so they should use the number 0. And you can see here we are back to some applications, our daily life applications. So you see, for example, we have a thermometer. I don't know if you see it here well. We can explain the application of thermodynamics, of the first law of thermodynamics in a thermometer. Is that the temperature of the thermometer indicates the temperature of a certain object. When the thermometer reaches thermal equilibrium with that object. So this is very clear, right? And here we know that we apply the principle of the 0th law. Yeah. Or here for the microwave. I don't know if you can see it. Microwave oven spins food slowly to cook food evenly and thermal equilibrium can be reached. Good. So the microwave also applies the application, also applies the 0th law of thermodynamics. And when we talk about temperature, when we talk about thermal equilibrium, we should also notice a phenomenon, which is the thermal expansion. Okay? So this is the tendency of matter to change its shape, its area, or its volume and density in response to a change in temperature. Why is that possible? Why the matter could change its shape, its volume, the density? Why is that possible? We know that there's a thermal expansion. There's a phenomenon called the thermal expansion. But why?
I guess as the temperature increases, so the atoms in the object is moving much faster and create more distance between atoms, so the volume should increase.
Very nice. This is very correct. Because when we raise the temperature of matter, of an object, we are adding the energy. So the atoms of that matter, of that object can move a bit further from one another than usual. Okay? And it can against the interatomic forces that hold every solid together. It means that it can expand, and how far it can move from one to each other, it depends on the substance. For example, when we talk about the solid, sometimes we cannot perceive it, we cannot perceive the thermal expansion. You can still measure it, but you cannot see it. But for the gas, you can see it, right? You can see it very often. So, for the thermal expansion, we have the linear expansion. You learned it already during the grade 10, so I will go very quickly in this part. We have the linear expansion, which is the increase or decrease in the length of a substance. And it could be calculated using this formula. So the change in the length is actually a result of the initial length times what we call the coefficient of linear expansion. So each substance will have a different coefficient of linear expansion times the change in temperature times the change in temperature. So we can see that, for example, the brass and the steel will have different coefficient of linear expansion. So under the same change in temperature, the two bars of brass and steel will have different change in length. Okay? Similarly, we have the volume expansion, and we can calculate it in the same way. We also have a coefficient of volume expansion that could be applied for each substance. Is it clear? It's too easy, right? Then we continue. Why is thermal expansion important? Could you give some example to say why? Why is thermal expansion important? Okay, we know that the substance, the object, can expand under the change in temperature, and in many cases we should predict it. We should predict it and we should anticipate. For example, I give you here an example of a truck bottling due to thermal expansion. You can see it's not a straight line anymore, right? It's not a straight line. So we should anticipate the thermal expansion of the steel. Otherwise we will break. We will break it. Or here, I don't know if you notice, there's the expansion gaps when you see in the road. This is to prevent any problem that might happen with the road. So when you go home, you can take a look. So we should prevent it. We should know, okay, how does the change in length, for example, of the concrete, and then we should take into account during the construction. That's why I say this is very important. Okay, during summer we can reach a temperature of 40 degrees Celsius very easily, but during winter, so it might decrease to only 7 degrees Celsius. There's a difference of more than 30 degrees, which is very important if you calculate the change in length of our concrete, of our steel. Is it okay? Now we move to the heat. So the heat is actually the energy transferred from one medium or object to another because of the temperature difference. So we know that the heat is the transfer of energy. Okay, this is the way we define the term heat. The heat is the transfer of energy from one object to another. That's why when there's no energy transfer, we say that the heat equals 0. And please remember the sign. A lot of people make mistake in thermodynamics because we also consider the sign, the direction. So, let's say, here I have my system. Outside, I have the environment. Good. When the temperature of my system is higher than the temperature of the environment, what do I have? I have a transfer of energy as heat from the system to the environment. So it means my system lost energy in the form of heat, right? Lost energy. And in this case, the heat is negative. Please remember, okay? The heat is negative. When the temperature of my system and the environment are equal, then there's no energy transfer as heat. I say the heat equals 0. Okay? And when the system receives the heat, we say that that heat is positive. So this is the by agreement. By agreement, we know that the heat is something we can measure. So it should be positive. Why you say that the heat is negative? This is by agreement for us to be able to calculate the energy of our system. So in our system, there's the energy in and there's the energy out. So the energy in, by agreement, we say that this energy is positive. If the energy is out, I mean the system lost energy, we say that that energy as heat is negative. Is it clear? Do not make mistake. Because after that you will have a lot of agreements, conventions. Quy ước đấy ạ. So sign agreement. Quy ước về dấu. Các bạn chú ý hộ tôi nhé. Trong thermodynamics là nó có rất nhiều quy ước về dấu. Và nếu như mà các bạn nhầm thì là cái bài toán của các bạn sai hết. Bởi vì các bạn đang giảng bài toán về you are solving the questions of heat transfer. Okay, mass transfer. The conversion between heat and work, for example, if you do mistake in the sign of the work or in the sign of the heat, then everything will be wrong. Is it clear? The question is heat an intrinsic property or extrinsic property of a system?
Is heat
Intrinsic or extrinsic property?
Well, I think heat is the extensive property because when you heat something, it can change the volume, the temperature.
so you say that is extrinsic?
Extensive.
Okay. Very nice.
So heat is an extrinsic property of the system, right? So please remember that. And what is the unit of heat?
Celsius.
No, this is for temperature. This one easy, right? What is the unit? Joule. Other units? Huh? Yeah, calorie. Other units? Have you ever heard about BTU? BTU, British Thermal Unit. Yeah? Where do we see it? Here. In Vietnam, where do we see it? The BTU. In your aircon, air conditioner. We still use it. For example, we say that, okay, this aircon has a power of 9 BTU. You can check in your air conditioner in your house. Yeah, BTU. Here, the system, the unit is more complicated than you think because before 1948, the calories or the BTU were used as the unit for the heat. There's a reason. Because before 1948, scientists did not realize that heat was transferred energy. Okay? And at that time, heat was measured in terms of its ability to raise temperature of water. That's why we have calories or BTU. So they measure heat as the amount of energy added to the water to raise its temperature. But then, before this date, after this date, we use joule more often because the scientists decided that heat is transferred energy just like work. So you can see that work also has the unit of joule and heat also has the unit of joule for that reason, because both quantities are transferred energy. Okay? So now you can understand why when we talk about heat there are a lot units. We have joules, we have calories, and we have BTU. So there's a reason behind it. Is it okay? And we can, from now on, we can convert from 1 calorie to BTU to joule. Okay? 1 calorie equal 4.1 something joules. When will be the next break? After how many minutes? Huh? Depends on me? No, I mean, we have the first break that should be taken around 8:30. The second break should be about 9:20. 30, 20 to 30. Okay, we have 20 more minutes to finish this part. Now we talk about specific heat. Okay? We know that we call the big C. I'm not talking about the supermarket, I'm talking about physics. Big C. Tôi không nói tới cái siêu thị Big C nha. We have the big C for the heat capacity of an object, and we measure it in joule per Kelvin. So when you see joule per Kelvin, what is the meaning of heat capacity? Or you can look at the name. What is the meaning of heat capacity? Okay, Vietnamese, nhiệt dung. What does it mean? Nhiệt dung. Nhiệt dung là một cái từ rất là trừu tượng, rất là nghe nó cứ lạ lạ đúng không? Nhiệt dung. Dung gì? Dung nhan là cái dung gì? What is the meaning of heat capacity?
Có phải là cái kiểu ví dụ là nước sôi ở trong giới hạn?
Is the amount of energy joule to raise the temperature of define volume to 1 degree.
Thank you. This is actually the amount of heat required to change, maybe to raise or to decrease. Okay. The temperature of a given amount of water, matter, by 1 unit of temperature. So I mean, maybe 1 degree Celsius, 1 Kelvin, or 1 Fahrenheit. But we know that this is the amount of heat required to change 1 unit of temperature. And with the heat capacity, we also have the specific heat. Here, the difference is only the involvement of the mass. Only the involvement of the mass. This one you learned already. You remember the equation Q equal mc delta T?
In a secondary.
Yeah, secondary school, you already learned it. Very famous. Q bằng mc delta T ạ. Đúng không ạ? Very famous. So the only difference is that we have the involvement of the mass here. So if we use the heat capacity, there's no the involvement of mass. With the specific heat, we should know the mass, and this is more practical because normally we always have to measure the weight, the mass of our substance. So, you know that to raise 1 kilogram of ice to 1 degree Celsius, it should be different than when you raise 10 kilograms, right? Here I can give you some values of the specific heat. This one for the solid. Okay. Okay, this one for the liquid. So what you see, there are a little differences in the solid. That's why you hardly see the change in the length or the change in the volume of the solid. But for example, for the liquid here, you see from mercury to water, there's a very big difference in the specific heat. So to raise the mercury by 1 degree Celsius, we need just a small amount of heat. But to raise water, for example, you need a lot of heat. Good. There's an important remark, is that when you use the specific heat of any substance, you need to know the conditions under which energy is transferred as heat. What do I mean here? I don't know if you realize during your high school or secondary school, you use only the C, right? C. But normally we should distinguish the CV and CP. CV stands for specific heat at constant volume, and CP stands for specific heat at constant pressure. The question is that when you do some problem, high school problems or secondary problem, do we use CV or CP? Usually we do CV or CP. When I say Q equal MC delta T, đúng không ạ? Khi mà tôi nói là Q và MC delta T đấy, là the formula that you learn during high school, cái công thức mà các bạn học hồi phổ thông đấy. So is it CV or CP? Is it?
I think CP.
Yeah, why?
Because in the Q equal, because in the Q equal MC delta T is there's no pressure in that specific, and I think the change is the mass of the volume is changed.
Actually, you are right, we use often CP because when we measure things, we always put it under the atmospheric pressure, right? Normally when we measure everything, we measure the heat and so on, we put it in the atmospheric pressure when we do experiments also. And for simplification during the high school, we also use mostly CP, not CP. And this can apply for solid and liquid because CV and CP of liquid or solid do not differ much. But for the gases, this is a real problem. When we change the volume of the gas or the pressure of the gas, we will see a very big difference between CV and CP. That's why we should differ the specific heat at constant volume and specific heat at constant pressure of the gases. We will talk about it later when we study the kinetic theory of gases. Okay, we talk about it. Now we go to the heat of transformation. Do you know that for any substance, there are two processes, what we call the melting and the vaporization. right? So any substance can be melted and any substance can be vaporized. When I say melt, it means we change from the solid state to the liquid state. And when I say vaporize, we change from the liquid state to the gas state. And we need energy to do it. Right? We need energy. And we call it the heat of transformation. The heat of transformation. For example, for the water, the heat of vaporization of water is 530 calories per gram or 2,256 kilojoule per kilogram. You should remember it. For the heat of fusion, we have another value which is equal to 333 kilojoule per kilogram. Good. And we could calculate the heat during the phase change using this formula. So if we know the mass, if we know the heat of transformation of the substance, we should be able to calculate the heat required for a substance to change its phase. Is it okay? So people who still play games, are you okay? Hope you do not play games. So, we take a few minutes to do a very small exercise to apply what I just discussing. Now, we have a cube of ice, for example. We know the mass of ice, which is 720 grams, and the temperature of ice is minus 10 degrees Celsius. We want to heat it, for it to become liquid at 15 degrees Celsius. At 15 degrees Celsius. Then how much heat should we provide? Okay? And if now we supply the ice with a total energy of 210 kilojoules as heat, then what will be the final state and also the final temperature of that ice? Maybe we need 2 minutes to solve these questions. A very common question, but you will see that it is a little bit more complicated than you think.
Teacher, I have a question.
question, do we have to multiply it with the heat capacity of water? Yes.
You have to use the specification.
Yeah.
Yes, answer.
Can you explain the way you find your answer because I do not calculate it. But if you can explain correctly the direction where to go, how to solve this question, then I think we can.
Okay, so in this question I really have from both to find the heat capacity of water. So I use the recipe to calculate formula to calculate the specific curve. It is a P equal MC delta T. So to the M is 720 grams, so I change to kilogram. It's 0.720 kilogram, and then I multiply with the Hertz capacity of water is 4,200.
When I say that, you
just have to explain the logic. Yeah, you do not need to mention about numbers and just the way. How can we solve it? In which direction can we solve it?
We the MC delta T.
So we have to calculate two stages.
exactly.
Firstly, that we have to count from the minus 10 degrees Celsius to 0 degrees Celsius.
Very good.
And then on the stage number 2, we will calculate the temperature from 0 degrees Celsius to 15 degrees Celsius. And then we will.
Something's still missing, right? Yes.
Furthermore, we need to calculate the heat of fusion that the ice change the state from solid to liquid.
The phase change.
We should take into account also the phase change. So we should break it into 3 steps, not only 2 steps. First step, here I give you the solution. But we should solve it by decomposing our problem into 3 steps. The first step, so we should calculate the heat needed to raise from the minus 10 degrees Celsius to 0. Okay? To 0. Because we know that in this case, we should use the specific heat of ice, not water, because we have ice and not water. Secondly, we should calculate the heat required to change the ice from 0 degrees Celsius to water at 0 degrees Celsius. Okay? Yeah. To melt all the ice, we need a lot of energy also, which is this one. And then, now we have water at 0 degrees Celsius. We need energy also to raise the temperature of water. Am I right? Then we should have this calculation. also. Then the total energy required is actually the heat of the 3 steps. The warming of the ice, the melting of the ice, and the warming of the liquid. Good. So we need around 300 kilojoule. For the second problem, if now we supply only 210 kilojoule, what will happen? We can compare it. So we see that our supplied energy is not enough to melt all the ice. Okay? Not enough to melt all the ice. So we know that the final state should be a mixture of water. If we calculate it, we should have 580 grams of water and still 140 grams of ice left. And since we still have ice, we know that the final temperature should be at 0 degrees Celsius. So this is the answer. So you see, the problem is quite easy. But when we analyze it, we see that it's more complicated than we think. We should consider it for 3 steps. Good? I think we can take a second break here and then we continue with the first law of thermodynamics. I hope that we can do it for today. We see each other in 10 minutes.
Thanh niên này đi rửa mặt đi, từ đấy giờ tôi chỉ thấy ngủ thôi. Ngon quá.
Linear. Thầy Dũng à? Calculus mới là thầy Khôi. Thế mà đứa nào bảo Linear? Linear hay Calculus? Linear thì là thầy Dũng, đứa nào bảo Calculus?
Hôm nay đổi lịch, thay đổi sang Calculus.
Linear hay Calculus?
Calculus.
Calculus! Thế đứa nào bảo Linear?
Bình thường là Linear thầy ơi, hôm nay mới đổi sang Calculus.
Calculus hay Linear?
Calculus.
Calculus thì là thầy Khôi.
Calculus là Linear thì
Bao nhiêu bạn vừa tạch sinh giơ tay lên này. Tớ sợ nhất là các cậu tạch sinh xong rồi các cậu lại tạch lý, thế là sinh lý không ra gì. Nên là những ai tạch sinh rồi phải cố gắng lý này nhá.
Thầy ơi,
em vẫn luôn yêu sinh lý.
Nó không là sinh lý có vấn đề.
Yêu sinh lý kém văn và hóa thì cho mình.
Giao lưu một vài phút nhỉ, cho Phi đang hết miếng bánh này. Còn bạn nào chưa biết tuổi nữa không nhỉ? Đây vẫn có một số bạn thắc mắc đây nhỉ.
thầy ơi em chưa biết nha, em sẽ đoán nhá.
Đoán đi xem nào.
Em chắc chắn một điều, hai số đầu là 19.
19, rồi.
Hai số đầu là 19. Ok. Số thứ ba là số ấy 8.
Rồi.
8 đúng không? 198 đúng không? Ok. Số cuối cùng này 5.
1985. Mình già thế được rồi à? Một số bạn biết tuổi mình rồi.
198 là đúng rồi thầy.
Đúng rồi. Tôi sinh 1986.
Ơi, sai có một số.
Một vợ chính thức. Hai con mèo. Chờ tớ tí, tớ còn đúng 2 tiếng thôi. Okay, let's back to reality. Can you close the door? We try to finish it on time.
Yeah, back to reality. So this is the last part of today. We talk about the first law of thermodynamics. What we want to answer is this question: how the energy can be transferred as heat and work between a system and its environment. So we know that heat is transferred energy. Work is also transferred energy. Then how does heat becomes work and work becomes heat? And how does the heat or work be transferred from one system to the environment? This is what we will mention in the first law of thermodynamics. Good. Maybe you do not remember the first law of thermodynamics, but you should remember the law of conservation of energy, right? Yeah. So in the law of conservation of energy, we say that the total energy of any isolated system which cannot exchange energy or matter is constant. Energy can be transformed from one form to another, but can be neither created nor destroyed. Okay, so this is the conservation of energy. We are quite familiar with this one. Trong tiếng Việt là gì ạ? Năng lượng không tự sinh ra, không tự mất đi, đúng không ạ? Mà chỉ chuyển từ dạng này sang dạng khác, đó là cái câu mà các bạn hay nói đấy. Về sau là thế hệ tôi thì bắt đầu phát triển thêm là định luật bảo toàn bạn gái này, định luật bảo toàn tiền này. Bạn gái không tự sinh ra, không tự mất đi đấy, mà chỉ chuyển từ tay thằng này sang tay thằng khác này, tiền nó cũng thế. Không biết là thời nay thì nó còn áp dụng hay không. But yeah. So this is the conservation of energy, the law of conservation of energy. And the first law of thermodynamics is only another way to formulate the law of conservation of energy, but it is adapted for thermodynamic processes. And in the first law, we distinguish two forms of energy: the heat and the thermodynamic work. Okay, the heat and the work. And it also defines what we call the internal energy of a system. And the internal energy is an extensive property. Okay, it does depend on the mass of our system. So this is an extensive property. Now we try to see the relationship between heat, work, and internal energy of a system. I have my system, which is a cylinder. So this is my system. Now I have a cylinder, a piston here. My cylinder is very well insulated, and it is placed on a thermal reservoir. I mean, it could provide the heat. Okay, a réservoir actually in French, and then English people borrowed this word and then they pronounce it in a very weird way, reservoir.
in French, a réservoir. Okay? It's just like English people say Wi-Fi, French people say Wi-Fi. Huh? It makes you laugh, right? But French people say it. Internet, they say Internet. Yeah. Weird. Now, inside of my very well insulated cylinder, we have our gas. Okay? We have our gas. This cylinder has a movable piston, which is this one, movable piston. And then on the movable piston, we have the electrode. Okay? For one purpose. We will know it later. We can control the heat transfer by adjusting the temperature. So we can control the heat transfer from the thermal reservoir to the gas inside our piston by adjusting the temperature. So now you could imagine our system, okay? And we know that the upward force on the piston is created by the weight of the electron. So it really depends on the weight, on the mass of the electron. And this one I already explained. Here we say that the gas starts from an initial state. It means that at the beginning it will have an initial pressure, an initial volume and an initial temperature. And it changes to a final state, final temperature, final volume, final pressure. We say that, okay, we perform a thermodynamic process. So, state, you know, the process, you know. We let our system perform a process. Then, how do we calculate the energy as heat? Knowing that if our system receives the heat, then we have a positive heat, right? We have a positive heat. Tôi thấy cái động tác mà các bạn gì nhỉ, dùng táp hay lấy gì nhanh phết nhé. Tớ lướt tới cái là thấy các bạn lạ thế, không biết là cái động tác gì. Lạ thế nhỉ. Thấy bạn nào cũng 100% được hạnh kiểm tốt. Cứ nhìn thấy màn hình thấy có bài của mình hay thế. Theo toán học là nó không tồn tại đâu, làm gì có chuyện là lại xác suất được 100% thế. Ở trên này nhìn rõ lắm các em ạ, các em có quay hay các em làm gì nhìn rõ đấy. Nhưng mà việc học suy cho cùng là việc của các em thôi. Okay, we have the thermal reservoir. We have if our gas receives heat, we will have a positive heat. If our gas loses heat, then that amount of heat will be negative. Good. The work also. If the work done by the system, it means that if here the gas expands and raise the piston up, then we say that our system does work. Is it okay? Then that amount of work will be positive. if the gas compresses by the force of the electrode, it means the piston is lowered, then the system receives work, or the work is added to the system. Then we will have a negative work. Please do not make mistake here. This is by agreement. We use this agreement. You can find it on another textbook. They might have another signed agreement. But from now on, we use this signed agreement. Is it okay? Please do not make mistake. When the system receives heat, then that heat is positive. But when the system receives work, that work is positive or negative? Positive or negative? If the system receives work. Hệ nhận công thì là công âm hay công dương ạ? Yeah, the work is negative. Please remember it very well, or you will make mistake. The work done by the system is positive. The work done on the system is negative. Okay? Done by the system positive, done on the system negative. Is it clear? Now we assume that the changes of the position of the piston occur slowly. Then we should have a thermal equilibrium for this system. So when I establish on the hypothesis, we should continue. Now, if we remove some electrode, then we move just a little bit of our piston. Okay? Then the piston will go through what we call a differential displacement, a very tiny change in the position. We call it a differential displacement. So this is the meaning of ds here. Okay, the differential. In mathematics, a differential is to say a very small change. Good. And it will have an upward force. Okay, the force will be like this. We can assume that this force is constant during this tiny displacement. Then we should be able to calculate this force, which is the product of the pressure of the gas and also the surface of the piston. Is it okay? So this is mechanics. Do you agree with me? We continue? Now, how can we calculate the differential work done by the gas during this displacement? Here we have the force. Okay? How can we calculate the work? Using mechanics. So, the differential work, I mean the very small change of work done by the gas during this displacement is actually the product between the force and this one. Okay, the surface, the change in the surface. Good. If we analyze it, it should be equal to P dV. Is it okay? P dV, because we have the area, we have the surface. Then we should know that the work done by the gas during a very tiny displacement is PdV. And we call the dV the differential change in the gas volume due to the piston's movement. Okay, the dV here, very tiny change in the volume of the gas. I think you should write it down, okay? Not just look at the slide, you can write it down. And then, when we remove enough the short to change the gas from the initial volume to the final volume, it means that we perform a lot of differential work, right? So each time when we remove a small amount of the lamp shot, we perform a small amount of differential work. How can we calculate the total amount of work? Yeah, we use in mathematics the integral. That's why we need Professor Khoi, that's why we need Professor Zhu to teach math for you, to serve for physics. We use the integral. Then now we know that the total work done can be calculated using this formula. So the integral of the differential work. So in mathematics, we know that the integral is to say the sum, right? Of every small change in the work. So we have, if we replace the differential work by PdV, we have this final formula. And this applies for every system. Every system, the work done by every system can be calculated using this formula. I mean the gas system, okay? Can be calculated using this formula. This is the integral from the initial volume to the final volume of PdV. Please remember it very well because we will see it more often. I'm sorry. So here, the meaning of this formula is that to evaluate the work, we need to know how pressure varies, okay, with the volume. Good. If the pressure is constant, so this is very easy for us. If we, for example, perform our process under atmospheric pressure, then we have a value, a fixed value of the pressure. We can take it out, right? We can take the pressure out from the integral. If this is not the case, for example, in our system, the pressure will change with the volume. Then this is not the case. We have to know the pressure. Good. And to express the process, the state of our system, we can use what we call a PV diagram. PV diagram. So a PV diagram is actually a pressure volume diagram. Yeah. Here we have the state number 1. Okay, I move on. Here we have the state number 1. Yeah, we do a process. We go to the state number 2. So, or we can say from the initial state to the final state. The initial state will have an initial pressure and an initial volume. For each dot in this diagram, we represent a state. Okay, một chấm ở trên cái diagram này là chỉ một trạng thái. For each node here, when we go from I to F, we do a process, and the area under the process, this one, represents the work, done by the process. So mathematically you understand why, right? Here, because we change the pressure, we change the volume mathematically. The sum of PTV should be this one. Good. So we can see that when we go from I to F, we can follow this process, or we can follow this process with the bigger work done. We can follow this process with the smaller work done. And we know that this work is positive because why we know this work is positive? Because the gas expands. Okay? The gas expands. So the final volume is bigger than the initial volume. Then mathematically we have a positive work. Good. Or we can have a net work done by the system, which is like this. We know this network is also positive. Why? Why this network is positive?
Đi ra rửa mặt mau lên, hoặc là đi về. Rồi tính ngủ từ tiết cuối đến từ tiết đầu đến tiết cuối.
Why we have a network is positive here? Tại sao thì nó lại dương ạ? Không ai biết ạ. Okay, please look. I'm sorry. Look at here. Firstly, the first process, it goes from I to F following this path. Then it returns in this path. Then the network from the first state, from the first process, is actually this area, right? Under the curve, this area. From I to F, so the network, the work I mean, is this area. So the network of this system is actually this area plus this area. Good. And this area, because the gas compresses, then the initial volume is bigger than the final volume. Then we should know that the work from F to I is negative. Is it okay? And this one is positive. The sum of this one actually is bigger. If we consider the absolute value, is bigger than this one. Then we should have a positive net work for the system. Is it clear to you here? I hope so. Then, to sum up, a system can be taken from an initial state to a final state by an infinite number of processes. And what we know also, the heat and work are path-dependent quantities. So it really depends on the process path. Okay? The work here, you see, really depends on the process path. If we go from the same initial state to the same final state, but following different paths, we will have different heat and work. But the quantity Q minus W is the same for all processes, and people already proved it experimentally. So what does it mean here? What does it mean here? Okay, we know that the heat is path dependent, the work is path dependent, but the heat minus work is independent of the process path. Okay? If it's the same, it's independent of the process path. For every process path, we have this quantity remaining the same. Then this one should represent a change in some intrinsic property of the system. And from now on, we call it the internal energy. And we write it the big E with the small e in E and T here. This stands for internal energy. So this is also the first law of the thermodynamics. We have the change in internal energy. Okay, we know when we say the change in internal energy, we use the symbol delta. And the delta is actually the sorry, I have to fix it here. It's the final energy, final internal energy minus the initial energy. Okay? And it is equal to the heat minus the work. So the internal energy of the system tends to increase if energy is added as heat, and tends to decrease if energy is lost as work done by the system. Once again here, I remind you, remember the sign agreement. Remember the sign agreement. Someone remember? Remember the sign agreement. So the heat is positive if the heat is added to the system, right? And the heat is negative if the heat is lost from the system. The work, in contrarily, the work done by the system is positive. So if we consider a gas system, when the gas expands, we have a positive or negative work. So when the gas expands, what do we have? A positive or negative work? Yeah. When the gas expands, we have positive work. I don't know, do you know it or do you guess or... But when we consider the gas, when the gas expands, we know that the gas does work to somewhere. And the work is negative if the work is done on the system. Here we mean that the gas compresses. Okay? When the gas compresses. we know that we have a negative work. Please remember very well this one and do not make mistake. We come back to our applications. Here there are a lot of applications that involve the first law of thermodynamics, and we can consider the thermal power plants, the coal power plant. Okay? So we apply the first law. Here the chemical energy is converted into thermal energy, and then converted into mechanical energy, then converted into electrical energy. So this is for the thermal power plant. For the jet engine, so the thermal energy is converted into kinetic energy. And then it will provide thrust for airplane. Or here for the heat engine, in your motorbike, for example, the heat energy is converted into mechanical energy to drive your motorcycle. Now we will consider 4 special cases of the first law. I hope that we could finish it in 10 minutes. 4 special cases. Firstly is the constant volume process. Easy, right? In a constant volume process, then the volume is held constant. It means that the work equals 0. No expansion of the gas, no compression of the gas, the work doesn't change, right? Because if you look at this formula, here, right? We know that when the initial volume and the final volume are the same, then this integral should be 0. Then we should have 0 for the work done by the system. So no discussion about it. Please correct it, okay? This is, when we say delta, is usually the final. I think I corrected it already. The final internal energy minus the initial internal energy. Good. Then in this case, when we have the work equals 0, what do we have? We will have the change in internal energy, which is exactly equal to the heat added to the system or lost from the system. So this is the first case, the constant volume process. Good. We can see some constant volume process in real life. So for example, the expulsion of heat in heat engine. Okay? So here the waste heat is expelled right after the vehicle receives power from the combustion. But since the piston is not moving, the volume of the chamber is unchanging and the pressure drops. So the expulsion of heat in heat engines can be considered a constant volume process. Or we can see the boiling of water in a pressure cooker. Okay, in a pressure cooker. Then when the heat is transferred to the container, we have a process which is done at a constant volume. Even we raise the temperature, the pressure, but the volume doesn't change. So we know that in this case, the heat, the change in internal energy is decided by the heat added to the system or the heat lost from the system only. Good. We continue. We go to the adiabatic process. Have you ever heard about this word? Adiabatic. In Vietnamese, what do we say? Lần đầu nghe. Ai cũng có lần đầu không em ạ? Ai cũng có lần đầu. Adiabatic. Đoạn nhiệt. Đoạn nhiệt là gì ạ? Nghe lạ nhỉ? Mình có đoạn nhiệt thì mình phải có đoạn nhiệt. Đoạn ở đây nghĩa là gián đoạn, đoạn tuyệt. So, adiabatic process, we call it Chujin, đoạn nhiệt. So this is a process that occurs so rapidly. So the system has no time to exchange the heat to the environment. So the heat will be equal to zero. Or our system is so well insulated. So there are two cases. Okay, two cases for the adiabatic process to take place. A system that occurs so rapidly. Okay? Not enough time for the transfer of heat. Or it is so well insulated. So well insulated. Then also no transfer of heat. Clear? I hope so, very clear. Then in this case, the work, the change in internal energy is actually equal only to the minus work. I mean, it is equal to the work done on the system and equal to the minus work done by the system. Okay? Here, remember once again the sign. Then if the work is done by the system, the energy, the internal energy will be decreased. So this is the adiabatic process. We can observe some adiabatic process in real life also. For example, when we have a vacuum flush, I don't know if you have one. So, because of the insulation is so good, we could say that we have a system that is close to an adiabatic process. If we consider the case that we do not insulate the system, an expanding and constructing sound wave can be a good example of an adiabatic process in reality because it happens so quickly. So the air will not have time to transfer its energy to the environment. Is it okay? We continue to the cyclical process, or we can call it also a closed cycle. For closed cycle, so we go from one state to another state, then from another state, we go back to the final state. And here, because the final internal energy and the initial energy is the same, we should have the change in internal energy equal 0. And in this case, the network done during the process must exactly equal to the heat transferred to the system. Okay? The work done by the system equal to the heat added to the system. We can also consider some cyclical process, but in reality, we do not have it. We do not have something that can really go from the final state and restore to the initial state. But we can apply the principle of a cyclic process for an engine. When we have the piston from the initial position, we continue. If we ignore the friction, okay, if you ignore the energy loss by the friction, then we consider the engine, our engine that we use every day is a cyclical process. And also the free expansion, the last special cases. What do we have? What is the free expansion? What is a free expansion? This is when everything equals 0. So we consider adiabatic processes. So adiabatic processes, Q equals 0, in which no work is done on or by the system. So the work also equals 0. Then everything should be 0. Can you give me one example, very famous example of free expansion? So we can consider this. Here I have a chamber. Here I have another chamber. Here I have my gas. Here I have the vacuum. And these two chambers are separated by a stopcock. What will happen if I open the stopcock? The gas here will occupy this volume, but without doing any work. Because this is vacuum. In this case, we have a free expansion. Okay? Now to sum up, we have the first law of thermodynamics that relates the change in internal energy of the system with the heat added to the system and the work done by the system. And we have 4 special cases. We have adiabatic, we have constant volume, we have closed cycle, we have free expansion. I think we can stop it for today, and then we will see some problems together during the tutorial class. I hope that you understand my first lecture. And if you have any question, please do not hesitate to ask me to come to my office or to ask me during the tutorial classes. I hope you enjoy my lecture today. Thank you so much.